AP. Today we're going to do the second part of section 2.1 on the derivative and the tangent line problem. We have already looked at some of these learning targets in the last set of notes. Just a quick review, looking for the slope of a tangent line to a curve at x or a specific point. We have looked at a couple examples like that, and some of your homework problems were exactly the same nature. Number 2, use the limit definition to find the derivative of a function at x. We have done that as well. Today we're going to look at how to understand the relationship between a derivative and continuity and determine places where the derivative cannot or does not exist. We're also going to briefly review how to write an equation, but we're going to do this using a calculus, the tangent line, and a specific point. And looking at a graph and determining what type of slope a tangent line would have to a particular point, we have already touched on that as well. So our focus today for this set of notes, you'll see several of the things, but 3 and 4 are our new targets. Okay, so today I want you to start writing using this slide. We're looking at different ways to write derivatives, like the notation. A derivative of a function or differentiation is the process of finding the derivative of a function. So when you hear me say the word differentiation, I'm referring to finding the derivative. And remember, derivative is the calculus way of looking at the slope of a tangent line to the graph at a particular location. There's different ways that our textbook writes down derivative notation. The first one is f, and this is just a little line above it, almost in an exponent position. F prime of x is how you say it. I'll top it out to the side. F prime of x. So when you see this notation, they're just asking you to find a derivative. Y prime, sometimes they'll use f of x, sometimes y. We've seen that in algebra. And then notice this says dy over dx. You would say it as the derivative of y with respect to x. So notice the top has the dy. dy dx is the same thing as find the derivative of y with respect to x. Then if you see d over dx f of x, that's saying find the derivative with respect to x of the function f of x. Find the derivative with respect to x. So the bottom part is the part that deals with respect to. And then occasionally you may see like a capital letter D and the X as like a subscript, and then some function here that you would read it as the derivative with respect to X of Y. So there's all kinds of different ways. Different authors of calculus textbooks will write derivatives. The top 3 that I have on the board are the most common, I feel like. I feel like these are the ones I use the most as well. So f prime of x, y prime, and dy dx is the derivative of y with respect to x. Okay, we're going to go back and review something we did in the last set of notes, which is the most important part of this section, is how to find a derivative using the limits and how they're connected. So it's the definition of a derivative of a function. And I've just topped it up on the board again. So to find my f prime x, which is derivative notation I shared with you on the last slide, the definition of a derivative is the same thing as a limit as delta x approaches 0 of, and remember this is the fancy calculus way of writing slope, y minus y over x minus x. So it's f of x plus delta x minus f of x over divided by delta x. And that's if the limit exists. So derivatives and limits are connected in this way. Anytime the direction says find or use the definition of a derivative, they're asking you to apply what's on the board to your problem. Okay, so we'll try another example. It says to use the definition, there it is again, definition of a derivative, to find the derivative of f of x equals x to the third minus 4x. So the first thing we're going to do is obviously write down this notation from the last slide. F prime x is equal to, we're going to do a limit as delta x approaches 0. And we're going to use f of x plus delta x minus f of x. Again, remember that's just y2 minus y1 divided by the difference in the x's, and that's going to be the change in x, or delta x. Now we're going to take this definition of a derivative and apply it to this function. So what we need to do, again, going back, reviewing something from the last slide, or the last set of notes, I should say, your job is to take each of these functions and evaluate them into this particular function. So here's how it's going to work. You're going to take the x plus delta x and substitute it in place of x every time you see it. Okay, so just like that. Okay, so that's going to be your first part. I'll put this in brackets. And then you're going to subtract off f of x, and so that part is just going to be essentially the same thing. F of x is x to the third minus 4x. And it's all being divided by delta x. And one thing I messed up on, I forgot to write down my limit notation, so when you put my equal out here, all of this stuff was supposed to go right there. So make sure you put that in your notes. Okay, so we're going to focus on the simplifying process right now, and I'm going to go ahead and take this minus sign and distribute it, so basically change the signs of both those terms while I'm at it here. And then I'm going to do this part next because it's easier. So I'm going to go ahead and say negative 4 times x. And then negative 4 times delta x. Alright, so the part we got to focus on right now, I left this to last because I knew it would take longer, is a binomial cubed. So the long way, and we're not going to really do this every single time because these problems can get lengthy, the long way is for you to visualize this written down 3 times. And looking at it, I'm going to bring my first binomial down. And you'll have to do FOIL twice kind of looking ahead, you'll have to do like this, x squared. Outside is x times delta x. Inside, also, same answer. And then last will be delta x times itself. Alright, let me show you another step here, and then I'm going to just kind of share the shortcut. So what we would do in algebra is we would combine like terms here, we drop our x squared down, and x delta x plus another x delta x, you're adding like terms. There are two of them. There's two x delta x's. Okay, and then from here, you would know in algebra to take the x and distribute it to all of those terms, and then take the delta x and do the same thing, and you would end up getting like 1, 2, 3, 4, 5, 6 terms right here, and then putting everything that looks the same together. Okay, so this is a good way to figure out what x plus delta x quantity cubed is. It just takes a while to do. And so what I'm going to do is kind of move ahead just to save some time, and I'm going to know ahead of time that x times x to the second is going to be x to the third. Anytime I have a binomial cubed, I'm allowed to basically take the first term and cube it and write it down. Then I'm allowed to think of it in terms of like there's going to be three of those next terms. So I'm going to go ahead and say there's 3 x squared delta x's. Again, this is based on patterns, and I didn't explain all of it, so this is the way to get there. It's just I'm trying to make this a little faster for note purposes. So 3x squared delta x, and then after working all this out, the third term would be 3x. 3x with the delta x squared. And then last would be this cubed. I'm going to go above this here. I really didn't leave myself a lot of room. And that would be like the last term, I should say. 1, 2, 3, 4 terms. That's what you'll get after you do all of this multiplication. Alright, let's try to make this look a little bit clearer. So what we're going to do right now is go through, pick out, what are like terms. You can see that there's an x cubed here, but a negative x cubed here. So those are definitely going to cancel for me, which is nice. I do see a negative 4x and a positive 4x. Those are going to cancel. 3x squared delta x. These two do not match because this one has a power of 2 on x and this has a power of 1. And this is different than this, so it looks like I'm going to have to just drop everything down. So remember, this is one term that I'm writing currently on the board. And then the next term would be 3x times delta x quantity squared. And then we've got delta x cubed, quantity cubed. And let's see, so I've got that term, I've got this term, oh, this one. I need to bring down my negative 4 delta x because it did not cancel. Alright, so I got all that. And now what I'm going to do is notice on top I have 4 terms, and all of them have, looks like a delta x. So I'm going to factor that out. And that's going to be leaving me with 3x to the second plus 3x plus, well, there's 3 here, but I factored 1 out, so delta x quantity squared, and then minus 4. You can always double check that using distributive property, make sure it matches the previous step. Okay. Alright, and now it looks like that's good. These cancel. And so we're still looking for the limit as delta x, what's happening to the height of the curve as the change in x is approaching 0 of this stuff. Okay, so I've got 3x to the second left plus 3x plus delta x quantity squared, and then minus 4. And so since I have simplified as much as I can, I'm ready to substitute this 0 in place of delta x. And so since I'm ready to substitute, I do not bring down this notation. I just go ahead and drop my 3x to the second down. We don't know what x is in this case. I do know delta x is we're trying to get close to 0, so we're going to do that. Substitute 0 in place of delta x, and then it looks like the derivative f prime x is going to be equal to 3x squared plus 3x plus 0, which I'm going to choose not to write down, minus 4. And so after much work, I found the f, let me scroll back up, the f prime x, the derivative, to be equal to the limit as delta x approaches 0 by definition, and the answer is 3x squared plus 3x minus 4. Okay, let me see something. Oh, okay. Just caught my mistake in the video, so let me go back. Okay, I apologize, guys. I want you to go back to this step in your notes. Let's fix this because I don't want to leave this wrong. When I factored out this delta x, obviously I didn't realize it until I got to the end. Delta x times 3x is not 3x delta x squared, quantity squared, so I should have put another delta x in here. Alright, so fix it in your notes. And again, I'm sorry, but at least I caught it. So I got that part. Now that means I need to put a little delta x in here. Okay, let's see. Oh, okay, that's going to change this. So now 3x times 0 is going to go right there. Okay, I'm going to get rid of this. 3x times 0 is just 0. And so my answer has changed big time. Now the answer, let's rephrase this, 3x squared minus 4 is the answer to the derivative of this problem. Alright, I'm glad I got that though. Alright, so 3x squared minus 4. Again, that's the definition, using the definition of derivative. Okay, let's use the definition, sorry about the typo there, use the definition of the derivative to find the slope at a point if we're going to just use the square root function. And so, let me do this so you can see this graphically. So we are basically looking at the graph, we know what it looks like. It starts at 0. If x is 1, the square root of 1 is 1. If x is, let's choose nice numbers, 4, then the square root of 4 is 2. If x is 9, we've done this problem in the past, the square root of 9 is 3. If I use negative 1 in for x here, the square root of negative 1 is imaginary, so that's why the graph doesn't have an x value of negative 1, and so forth. And we know from algebra that the graph kind of curves in that direction. Use the definition of a derivative to find the slope at a point. And so, first of all, they want me to find the general definition, the general derivative, remember the notation. Second, they want me to find the slope at a specific point, when x is 1 and when x is 4. So remember from the past what that basically means. They want me to take this picture and look at it from the perspective of, well, what kind of tangent line could be drawn when x is 1? What would the slope of that tangent line be? And I can tell just by me doing this it's going to be positive, but I have to find the precise answer. And then they're asking me to find the slope of f of x at 4, 2. Well, here's 4, 2. They're wanting me to picture another tangent line drawn right here where it touches that point and the graph of f of x at the same time, and find the derivative of it, or the slope of it. And I can tell it's going to be positive. I also can tell just by the direction that this answer is going to be different than this answer. And remember, that's the whole purpose in derivatives. Every single point you randomly select on your curve, you can draw a tangent line that precisely fits that position, and the slope of that line will be different. So when they ask you to find a general derivative like f prime x, they're just asking you to find the equation that's going to help you find all the other slopes. And then C wants us to discuss behavior of f at 0, 0. Alright, so for part A, you would have to go through and actually do the definition of what we just did a second ago. So limit, and that's delta x approaches 0, of f of, it's going to be x plus delta x minus f of x over delta x. Okay, so it's going to take a few steps and just hang in there. That's the nature of the problems. We just want to make sure that we don't lose our place here. Just hang in there. Alright, we are going to take x plus delta x, substitute it in here. So we need to evaluate f of x plus delta x, and then we need to subtract off f of x. Alright, let's focus on this one first. Okay, that's what it would look like. And then minus sign. And then f of x is just the square root of x. That's the function we're dealing with. And there we go. Alright, now think about it in these terms. This is where I am right now. If I were to substitute 0 in place of delta x, then this would be the square root of x minus the square root of x, which would give me 0 on top and 0 on the bottom. That's an indeterminate form from the past, which will not work. So we are going to have to be creative and use some things that we've learned in the past. When we have radicals, we know we can rationalize. So that's going to be where we should go next. And you want to make sure we do that on top and bottom, because essentially we're just multiplying by a fancy way of writing 1. This is a really fancy way of writing 1. Remember to use the conjugate, and so you're changing the sign only. Alright, let's see how this goes. We're going to focus on the numerator first, of course. We need to multiply this binomial, see that as a binomial, times this binomial. They are conjugates of each other. So we know ahead of time that like the outside and the inside, they should cancel. When I use a positive square root of x times this and a negative square root of x times this, it's the same answer. And so it's going to cancel. So that's going to help us speed it up a little bit. Let's just go back and do the first and last. So the first term would be the square root of x plus delta x times itself. The square root of something times itself is always going to be that radicand back. You've heard me say that a ton of times over the past couple years. And again, we're allowed to skip the O and I because they cancel. So let's go to the last, excuse me, which is here. Negative times positive is negative, and the square root of x times the square root of x is technically the square root of x squared. But again, that's just going to leave me, as I simplify it, it's going to leave me with the radicand. Okay, denominator. I'm going to go ahead and just copy down the delta x and also copy down this binomial. There we go. And let's look at the top. The top is going to give me x minus x. Ooh, that's going to cancel for me. And I see a delta x left. The bottom, I'm just going to recopy. Took me a second. Alright. Here we go. And the delta x is going to cancel from top to bottom. Okay, so we're going to be left with the limit as delta x approaches 0. There's nothing on top, so it's going to be a placeholder there. 1 over the square root of x plus delta x. Plus square root of x. Okay, now we're ready to substitute. Let's put 0 in place of delta x and see if this is going to work for us. So 1 divided by square root of x plus delta x becomes 0. Okay, that's where I am right now. And then we know how to add radicals. They have to have the same radicands. You just combine what's in front. So I finally got to the first part. 1 plus 1 is 2. So 1 divided by 2 radical x is what, we've worked on it so long, we may have forgotten what we're doing. I hope not. But it's f prime x. And so this is the general rule for derivative. Okay, so we're going to go back up here. Believe it or not, I'm sorry to tell you, we have only done part A, but it'll go faster when you follow my example and you're trying to do it on your own. It's just taking me some time trying to explain everything. And that's the challenge of doing AP this way, but that's the cards we're dealt. We're going to do the best we can. For part B, we now find the slope of f of x at 1, 1, and 4, 2. And so what that again means is, imagine the tangent line drawn here. We're trying to find the slope precisely. So for part B, you would go here. Let me go right here and show you quickly. At the point 1, 1, you would take your function, and this is the way you would write it down in your homework. I want you to do f prime to show me that you're using the derivative, and you're going to substitute the x value. Okay, so f prime 1, you're going to put 1 in place of the x, just like that. And the answer there is 1/2. So, back to the graph. That means if I can imagine a little line drawn like right in there, the slope of that tangent line is 1/2. Now it says to find the slope of f of x at 4, 2. So, go back. Still on part B into our directions, our point changes to 4, 2. So we're going to use the general derivative for the function f. We're going to go f prime, evaluate it when x is 4, and see what happens. Okay, so that's going to give me 1 on top and 2 times the square root of 4, which is 2. So that means this part is going to be 1/4. So when x is 4, the slope of the tangent line is 1/4. 1/2 and 1/4 obviously are different fractions, and so kind of leading back to my comment I made earlier, I knew these were going to be different answers, I just didn't know exactly what they were. So this slope is going to be 1/2 and this one's going to be 1/4. Okay, I've done part B. Part C, discuss behavior of f at 0, 0. Okay, so now basically they want me to say, like, what's happening if we're going to look at it on the graph at the origin? Well, part C would mean you go to your derivative, treat it just like B. Put 0 in place of x and see what happens. Two times 0. Uh-oh. Uh-oh. Okay. I, right now, cannot give an answer. So my slope, don't forget this means slope. My slope is undefined. Okay, think about that. Algebra terms, my slope is undefined. That means right here, when x is 0, the only way I can draw a tangent line, undefined slope, is vertical. Discuss behavior. So if my slope is undefined, when I put 0 in place of x in my derivative I found, then that must mean that f of x has a vertical tangent line. And that's what you would write for part C. So since the slope is undefined, f of x has a vertical tangent line. Okay, now tying it back to the calculus, I want to make sure, because you got to remember there's all kinds of things, like specifics you got to remember. Not only does the slope, when it's undefined, mean it's going to be a vertical line, tangent line, but also imagine if I were to take this, I'm going to tie all this back together. Hopefully you'll have a light bulb moment here. Remember, derivative is related to the limit. Okay? I'm going to change this to x. So, let me ask you this. If this is the function, if this is the derivative, and you were to put 0 in place of x, do the limit, then 1 over 0, the limit of that is going to go to infinity. So since the limit is going to go to, remember me saying in the past, when you have a number divided by 0, it's going to go to infinity. When that happens, when the slope is undefined, the limit's infinity, then that's what makes it be a vertical tangent line. And we've done that the other day, right here. For vertical lines, if the limit as delta x approaches 0 is either infinity or negative infinity, then you're going to have a vertical tangent line. And also notice this. Let me go back. Sharp points. That's my position. That's my starting position. Okay, and so there's nothing else over here. Because of all of that, that's why, or that's how you would discuss the behavior for F. So I hope that made sense with like trying to connect all the pieces together and make you understand the mathematics, the calculus mathematics behind it. Oh, and one other thing on this slide. Promise we're getting close. One of the learning targets, and I need to show you this because it's also going to be in your practice set, it's sometimes they ask you to write an equation for the tangent line. And so I'm just going to pick one of the ones we've already done. Okay, so you know how we found 4/2? We found the slope at 4 to be 1/4. When you're doing an equation, write an equation for a tangent line, in calculus, I want you to use the point slope form. And we use this a whole lot in algebra. We use slope intercept form more, but I want you to use this because that's what the AP exam uses a lot. And so just a reminder, it is y minus y sub 1 equals m times x minus x sub 1. Okay, so what does that mean? Well, this is the formula to write an equation in point slope form. The name gives it away. You must have a point and you must have a slope. We know where the slope goes. Hopefully. If not, we're all in trouble. Okay, and we know that points have x and y, and so the y1, x1, that's where your point's going to go. So very simply, okay, gave you the background information. This is what I want you to do. If it says write an equation for the tangent line at 4/2 using all of this problem, we just found a few minutes ago that the slope was 1/4. We just found that. And I'm asking you to consider the tangent line at a specific location, 4/2. Then all you have to do is fill in your pieces. Y minus y1, well, there's my y, so it'll be 2, equals my slope, 1/4. Okay, parentheses, and then my x minus 4. So this is how I want you to leave it. And I know that might be hard for some of us because we are so used to writing y equals mx plus b, but the calculus prefers it in this form. So anytime it's asking you in your practice set to write an equation, and they may even do the same thing I did. They may give you an equation, and you might want to look at it graphically to kind of help you visualize it. If they're just asking you for the derivative, you need to go through the definition, go through all these steps, simplify, and find what it is. Then they'll probably ask you about a specific point. Okay, so if this is the general definition for slope, well, what's the slope going to be when x is 1? What's the slope going to be when x is 4? Maybe what's the slope going to be when x is 0? They'll ask you questions about that, and then possibly about the equation. All right. Last thing I promise. Differentiability and continuity. A function is not differentiable, which means sometimes a function doesn't have a derivative, but we know that based on the last example, at a point in which the graph either has a sharp turn or a vertical tangent line, or it's just discontinuous. Kind of paused too early there. So there are some functions out there that don't have derivatives. Based on the graph, if there's a sharp turn in the graph, if there's a vertical tangent line, or if the graph's like discontinuous, like a step function, you can't give me a derivative for it. Okay. Theorem 2.1 in your textbook says that differentiability implies continuity. Meaning what? Meaning that if I can find a derivative of a function, then that is implying to me, telling me that the function is continuous. That there is not a discontinuity. There's no hole or asymptote or vertical tangent line or sharp turn. It might just be a polynomial graph, x to the fifth. That has a derivative. That's important to know. So if f is differentiable at x equals c, and c can be any number, in other words, if I give you a function and you know, oh, okay, I can find the derivative of that at x equals some number, then that means that f is continuous, guaranteed. The reverse of my last statement is sometimes but not always true, unfortunately. Sometimes graphs are continuous, but they're not, you can't find the derivative at every single point. Sometimes graphs are continuous, but you cannot find the derivative at every single point. Okay, so it works forward, but it does not work backward. The last example that we spent a lot of time on is a prime example of this. This is a continuous function, for sure, continuous from 0 forward, 0 to positive infinity. However, it is not differentiable at 0. I'm going to say that again. A function, if you can find the derivative for it, automatically that means it's continuous. However, the reverse is not always true. Sometimes continuous graphs don't always have derivatives. You can't find the slope of a tangent line because there might be a sharp turn, vertical tangent line, and so on. So I've said that several times, trying to repeat it, drill it in your head. That is super important, and we need to make sure that we understand what that's saying and grasp that in our head. Theorem 2.1, and you need to read through it in your textbook, and that will help solidify your understanding. You need to always make sure you read it, especially this year, since you're getting less face-to-face interaction with me. Alright, so there are 5 learning targets, and what we did today was writing equations. I kind of tied in all of them, but writing equations of tangent lines to a specific point, trying to understand the difference between differentiability and continuity, using a limit definition, slope, looking at a graph, all the kinds of good things like that. So that is it for section 2.1. And yes, it took us 2 days, 2 videos, and this one's very long, but that's, again, I don't know an easier way to do this. If I did, I would do it. Okay, so hopefully me taking the time to do this is helping you, giving you a better chance of understanding the material. So give it your best try, and on Zoom we'll come back and try to tie up loose ends, ask questions, make sure we're where we need to be for AP right now, and then keep moving on. Okay.